Good morning, everybody but Lincoln. Welcome back to Galois Theory. How y'all doing today? Glad to hear it. All right, plan for today. We're going to talk about a couple special types of field extensions called normal extensions and separable extensions, related to which are going to, by our powers combined, make Galois extensions. So that next week we're ready to talk about the Galois correspondence and get to the real heart of Galois theory coming next week. Plan for today, let's see, office hours. Got my usual office hours the next few days. Homework, don't forget you all have a homework set to do on Tuesday. The exam. Pass back the exam. I should have solutions posted later today. For all nice job. Be happy to talk to you about your exam if you have any questions, comments, or concerns relating to it.
But don't talk about it with other people in front of you.
That'll make me nervous, yes. Apparently. Any questions or comments before we get started for today? All right. I had a 105 student come up to me today and say, Dr. Gerstle, on this exam you gave us, because they had an exam today in class, I agreed to prove propositions, I agreed to look at axioms, I even agreed to arrive at logical contradictions, but graphing functions, that's where I draw the line.
How did you tell the joke to the 105 student?
It's essentially the same.
I was just wondering if you had another class's student who came up to you for them.
Oh, no. I think for them I just that phrase. I forget.
I have 415.
Something. All right. Let's go back into. Let's talk some more about Galois groups then. So, Lydia, I'll email your exam later today. Last time we defined what it means to take the Galois group of an algebraic field extension. Where we said that the Galois group of the extension L over K is the group of automorphisms of L that fix every element in K, meaning the set of all phi that are isomorphisms from L to itself, where phi maps any element in K specifically to itself. So elements in L outside of K may or may not get mapped to themselves. And similarly, we said that if you want to just take the Galois group of some polynomial within K, just take the Galois group of the field extension where L is just some splitting field over K. And by kind of our uniqueness of splitting fields, this becomes a well-defined thing. Question: what did we say was the group operation? It's the Galois group part.
I remember you said function, like composition.
It is indeed function composition. So the fact that it's a group relies on things like, for instance, the composition of isomorphisms is an isomorphism, etc., etc. So last time we looked at a couple examples, or a few examples of actually computing some Galois groups. Hi James. Start off by doing one more of those today. So let's do, just for funsies, 2x cubed minus 2. This one's not actually typed out in the packet, but it is a fun one.
You don't have the packet yet anyway.
Oh, well, that sounds like a you problem. For the automorphism packet from last time?
No, I thought we were done with that one, but
Oh, well, surprise. Let's compute the Galois group of this thing. So, according to our definition, when you have a polynomial rather than some explicit field extension, we can assume that our base field is going to be Q, in this case. And our L, our extension of Q, needs to be a splitting field for x cubed minus 2. So in other words, a minimal field extension over which x cubed minus 2 will factor into linear terms. Take a look-see. So first of all, if we want this to have 3 roots. What are we going to have to add to cube? Because to start with, this thing doesn't have any roots. Arthur?
Well, good first one would be cube root of 2.
Cube root of 2? Neato burrito. That'll give us 1 root. Factor. We'll have 1 linear factor of x minus cube root of 2 if we tack that on. Fortunately, I don't think cube root of 2 is enough here. We're going to need to add something else here in order to be able to get other roots. Andrew? E to the 2 pi I over 3. Holy smokes, where'd that come from?
It's a number that when you do this one.
Yeah, you're taking a 3rd root of unity, in other words. The reason being that over the complex numbers, x cubed minus 2 has roots of cube root of 2 e to the 2 pi I over 3 times cube root of 2. And what's our last root? Rose?
E to the 4 pi I over 3 times the cube root of 2.
E to the 4 pi I. Keeping in mind, e to the 2 pi I over 3 is just a complex number. It's cosine of 2 pi over 3 plus I sine of 2 pi over 3. Those of you who remember your trigonometry, figure out what that is for me. But it's a complex number that when you cube it, you get 1. Because when you cube that, you get e to the 2 pi I, which is famously equal to 1. So if these are our 3 complex roots, and in order to get a splitting field for x cubed minus 2, you need to be able to adjoin each of these to q, which you can get from just taking cube root of 2 and e to the 2 pi I over 3, which will give you all these roots, and also not give you anything unnecessary in order for this to still be a field. So in essence then, finding the splitting field finding the Galois group of x cubed minus 2 corresponds to finding the Galois group of this field extension, L over K. Yo.
Couldn't you do this roots of unity thing? You could just generalize that for any single degree kind of polynomial where it's just like x to the 4, x to the 5 minus some constant plus some constant.
Yeah. And if it's something where your polynomial is literally just x to the n minus c, you'll always get a very similar looking group.
Yeah, because we did x to the 4 minus 2.
Extension at least.
We did x to the 4 minus 2, but we didn't express it as roots of unity, but we could have.
Because 4 is a nicer number than 3.
That's numbers.
4 is a nicer number than 3. It is true. So let's look for automorphisms. So in other words, let's look for elements phi that lie in our Galois group of L over K here.
So not just automorphisms then.
Not just automorphisms, but ones that fix K specifically, which by a theorem we said last time ends up just being all automorphisms
Right,
of L.
because we're over Q.
If you recall, last time we had a theorem that says any automorphism,
Over Q.
any elements in the Galois group, or any automorphism of L, if L is an extension of Q, is automatically going to fix Q.
I do remember that
So,
when I think about it.
so what do we need to do here? Well, turns out we only really need to check where 3 elements get sent in order to fully determine what the automorphism does. You need to go where 1 gets mapped to. Because if you know where 1 gets mapped to, that'll tell you any element in Q gets mapped to. We need to know where cube root of 2 gets mapped to. And we need to know where e to the 2 pi I over 3 gets mapped to. And if we know where these 3 elements get mapped to from some automorphism on L, that'll automatically tell us where everything in L gets mapped to by this automorphism.
We don't need to look at e to the 4 pi I over 3?
No, because that's just e to the 2 pi over 3 squared. And since an automorphism has to be a homomorphism with respect to multiplication, phi of e to the 4 pi I over 3 is just going to be phi of e to the 2 pi I over 3 quantity squared. Does that make sense?
Mm-hmm. Which is also why
Let's actually write that down.
Which is also why we don't have to append all the cube root of 2's to the e's.
Correct. Yeah, well, which is also why we don't need to do, for instance, cube root of 2 squared. Or 2 to the 2/3. Because if you wanted to know where does this get mapped, well, it turns out this is just e to the 2 pi I over 3 quantity squared. Using the fact that phi is a multiplicative homomorphism, that ends up just being phi of e to the 2 pi I over 3 multiplied by itself. So if you know where phi maps e to the 2 pi I over 3, that'll automatically tell you e to the 4 pi I over 3. And by very similar reasons, if you know where cube root of 2 gets mapped to, that'll automatically tell you where cube root of 2 squared gets mapped to. So these are really the only things, choices we have, and our choices for where these three elements get mapped to will determine the whole shebang. So, let's take a look at each of these. Isaac.
I think for the second two, the third root of 2 and e to the whatever, it seems like, well, they both have a minimal polynomial of x to the third minus 2.
What does?
Those numbers in Q.
What are those numbers?
The square root of, or cube root of 2,
Thank you, was that so hard?
and e to the 2 pi I minus over 3.
Those have the same minimal polynomial? One is x cubed minus 2, one is what, x cubed minus 1. I don't think these have the same,
okay.
I don't think these have the same minimal polynomial.
Regardless,
Cube root of 2 e to the 2 pi over 3 times cube root of 2 will have the same minimal polynomial as cube root of 2, but not e to the 2 pi I over 3 by itself.
yeah. Regardless, it seems like they'll be mapping to each other, and then we can fudge the constants to make it work.
Yeah. So if you remember, we had this theorem yesterday which says if you have some automorphism of L here, roots of a polynomial have to map to roots of the same polynomial. That was a theorem we had from last class. So in other words, cube root of 2 is a root of x cubed minus 2 over our base field, the rational numbers. Therefore, cube root of 2 should map to another root of x cubed minus 2 somehow. So with that in mind, what are the possibilities for where cube root of 2 can get mapped to? Lincoln?
e to the 2 pi I over 3 or e to the 4 pi I over 3.
Or itself.
Times cube root of 2, I hope
Yes.
you mean?
Yes.
Yeah. Or itself. Yeah, so we end up with three possibilities for where cube root of 2 can get mapped to. It can get mapped to itself, it can get mapped to shebang, and it can get mapped to this. The three roots of the same polynomial in Q. How about e to the 2 pi I over 3? So that's a root of, what, x cubed minus 1? Is a rational polynomial. Andrew?
X squared plus x plus 1. Also, that's the minimal, because we get the 1.
Dang it, you're spoiling my point. I was hoping someone was going to say this could map to 1 and I was going to pounce on them. True, this is not the minimal polynomial, but it is a polynomial.
Sorry, Dr. Gristle, I've already looked at the homework, that's why we know this.
That's true.
Good, I'm glad you're looking ahead. This is very much a question like this on the homework.
That's not.
So, yeah, you can either map this to roots of x cubed minus 1, which will give you e to the 2 pi I over 3, e to the 4 pi I over 3, and 1. Turns out, 1 is not an option for where e to the 2 pi I over 3 maps to. Why is that? Matthew?
I'm assuming because only one can map to one.
Yeah, we know 1 has to map to 1 because by definition, every element in the base field K, in this case every rational number, necessarily has to map to itself. And then in order for phi to be a 1-to-1 function, e to the 2 pi I over 3 can't also map to the same thing. That's a good way to describe it.
so fits.
So we end up with this as our list of possibilities.
That's an if. Oh, it doesn't work the other way. So does that fact show that x to the third minus 1 is not the minimal polynomial? Or do we not know?
Yes,
Oh, it does.
but that'll be made more clear from a theorem later today.
Okay.
So I'm not going to say quite yet, but it turns out that has something to do with like splitting field normal extensions. We're going to have a nice theorem that tells us that that would be the case. Yeah. The theorem we had last time that said roots of polynomial have to map to other roots of polynomial. Ultimately, if you apply that to the minimal polynomial, it really says that roots of the minimal polynomial of e to the 2 pi over 3 have to map to other roots of the same minimal polynomial. Or irreducible polynomial is perhaps a better way to say it. Alright, so 1 has to map to itself. Cube root of 2 has 3 options for where it maps to. E to the 2 pi over 3 has 2 options for where it maps to. What's our Galois group going to be isomorphic to? Andrew? D3. Emily Rose?
Well, that was what I was going to say.
Lincoln?
I'm not sure about that one. I don't know that it's D3, but
Oh, controversy. What do you think? What were you going to say?
well, I mean, they don't necessarily both. Okay, I think D3 is probably right.
D3 is correct. However, I want to do an example with S3, so let's do S3 instead, which is isomorphic to D3, so either one is a correct answer here. Yeah. We know we have 6, so we have to have some group of order 6. Turns out it's going to be the non-abelian one, because I have the cube root of 2 to here, and because, well, function composition ends up being non-commutative in this case. So let's actually show that Galois group of q minus 2 is isomorphic to S3. I want to bring up S3 because we haven't talked about the symmetric group in all, actually, we talked about it at all this semester. I'm not sure we have. But it's going to be one that comes up and plays an important role in, say, I don't know, proving an insolvability of the quintic with radicals.
Ooh.
So let's remind ourselves of what this is. So what is the symmetric group Sn on n elements? What are the elements that group look like in general?
The ones I had the hardest time understanding last semester, it ended up being permutations of numbers.
Yeah, permutations of numbers 1 through n. So in this case, permutations of the numbers 1 through 3. Which, yeah, it's very kind of counterintuitive the first time you encounter it, getting used to the notation and such.
I hope I remember because that was a lot of hours.
Glad to hear it. So, what are the elements in S3? There are 6 of them. James?
Let's see if I can remember this. First, there's the doublets. There's 1, parenthesis 1, 2, parenthesis 2, 3, parenthesis 1, 3.
Yep, the transpositions, the permutation that swaps 1 and 2 and leaves 3 alone, because it isn't mentioned. The permutation that swaps 2 and 3 and leaves 1 alone. The permutation that swaps 1 and 3 and leaves 2 alone. Parker?
Then we have the triplets, the ones that go 1, 2, 3,
Aha.
and then 1, 3, 2.
Indeed, the ones where 1 maps to 2, which maps to 3, which maps back to 1, and 1 maps to 3, maps to 2, which maps back to 1. I said there's 6 of them, we have 5, so what's missing? Matthew?
The identity.
I was going to say, group needs to have an identity element. So we also have the permutation that just does nothing. Every element gets mapped to itself.
Right.
So I want to define a isomorphism from the Galois group to S3 specifically. So what can we map to what?
Map 1 to the identity element.
Technically, can't map, we can map the identity function, so the one that maps 1 to 1, cube root of 2 to cube root of 2, e to the 2 pi I over 3, e to the 2 pi I over 3. Oh my gosh, this function can map to this other function. We have a function taking functions to functions. Yeah, that can map to the identity permutation. Which makes sense. We need the identity element in this group to map to the identity element in that group. So this is the identity element here, the automorphism of L that just leaves everything alone. Maps to the element of the symmetric, the permutation in the symmetric group that leaves everything alone. What else? Matthew?
I think it's kind of obviously split to 3 and 2, so it's like kind of the same thing over here where you have 3 doublet groups almost, and you have 3 in the 3 root 2 groups. So I don't know how much it really matters what you're mapping to which and how they operate necessarily, but
It matters somewhat.
I feel like you could just go 3 root 2 and just map it to 1, 2, and then and just keep on going down the list, and then
Problem is, we can't just map 3 root 2, cube root of 2, because cube root of 2 is not an element in this group.
oh, okay.
We need a function. We need
Yeah.
one of these
So-
functions. So like we need to have a function that maps 1 to 1, cube root of 2 to one of these things, e to the 2 pi over 3 to one of these two things. That entire function can map to, say, one of our 2 cycles or one of our 3 cycles. But we can't just map cube root of 2 on its own, because cube root of 2 is not an element of the Galois group. It's one of the things getting acted upon, not one of the actors. Does that make sense?
Yeah.
It's sneaky and subtle because we're not used to thinking this way,
Right.
but it's definitely the case. I see.
So to actually accomplish that, all you need to do is say, the way you listed them out, we've already taken care of the first column. If you choose all the elements from the first column, that's the identity function. If what? That's
Yeah.
Yeah. So then, now we choose the second thing in the second row, e to the 2 pi I over 3 square root cube root 2. And then don't change what you're doing on the last one. That states the identity. So that you've only made one change. So that's one of the 2 cycles.
Aha!
And then repeat that, make one change in each, you get 3 of them.
Yeah. If you think about it, this permutation keeps one of our roots, 2 of our roots the same, changes this one root to something, and why does this have to map to a 3 cycle and not a 2 cycle?
Oh, because it has to go around in on the third root's unity. The squared one has to go to e to the 4 pi I over 3 square root or cube root of 2.
Yeah, in other words, it's because this is a function of order 3. If you do this function 3 times, you basically multiply by e to the 2 pi I over 3. If you do it once, that'll map here to here. You do it again, that'll map e cube root of 2 to here. You do it a third time, it'll end up back where you started. And then everything else after 3 times will end up back at the end where it started to, because it's fixed. Therefore, this is a function that if we compose 3 copies of it with itself, would give us the identity. And so if we're defining an isomorphism, we better be mapping this to some element in S3 that if you composed it 3 times with itself would be the identity element. 2 cycle doesn't work in that case, because if you take a 2 cycle times itself 3 times, we'll just get the 2 cycle back. But a 3 cycle, that would be the identity.
So then, that would mean that for the next one, 1 maps to 1, cube root 2 maps to e to the 4 pi I thirds cube root 2, is gonna also map to the other 3 cycle.
Hold on, let's finish this one first. So Isaac, you said you wanted this to map to a 3 cycle?
Yeah,
Which one?
1, 2, 3.
1, 2, 3.
Doesn't matter which one.
If we had listed,
Turns out it doesn't matter.
if we had thrown in, say we had made the third or the second extension that we did square root or cube root of 2e to the 2 pi I over 3.
Sure.
You can actually write the cycles out
You'd end up getting, yeah,
with those elements.
you'd end up getting the same thing, just written slightly differently, because essentially choosing to define our automorphism by what it does to these elements versus what it does to these three elements is a different way of defining the same elements in this Galois group. You're still going to get 6 functions. They're going to be the same functions. It's just that the way you're kind of defining them is a little bit looks different. But in fact, it would give you the exact same 6 automorphisms, and you could similarly define maps that define an isomorphism from here to here.
It just makes it clear which combinations are permissible.
Sure. If you would so prefer. Now, technically, there's infinitely many ways of defining a phi here. I like this way because I think it's the simplest and involves me writing out e to the 2 pi I over 3 the fewest number of times, or cube root of 2 the fewest number of times. But that's just me.
So I'm not remembering exactly how S3 works. Are we supposed to read from right to left? So
We do when we multiply cycles in S3.
Okay, but is the element 1, 2, 3, is that saying 1 maps to 2 maps to which maps to 3, or is it
Yes.
saying?
Mhm.
And then-
So this is a 3 cycle. 1 maps to 2, 2 maps to 3, 3 maps back to 1 as a function
So within
from the set 1, 2, 3 to
okay,
itself.
so within the element itself, we read from left to right, but when we multiply them by each other, we read from right to left.
Which is what gave, I think, Emily Rose so much headache last semester.
So hard. Okay.
I found a way to write it out that helped make a little bit more sense of it.
And also, not to quibble, but we can write any of the 3 cycles as a product of 2 cycles, yes?
This is true.
So, in theory, wouldn't we want to start with the 2 cycles and then just compose the elements they map to with each other?
You could. There's lots of ways of doing this.
Just
This-
it might be slightly faster.
I was gonna say pick a 2 cycle next, and then say our choice of what maps to this specific 3 cycle, and our choice of what 2 cycle we want to map to is going to determine the other 3. But if you want to start by determining like a couple of the 2 cycles and then doing it that way, you could certainly do that instead. Matthew,
Why are we mapping e to the 2 pi I over 3 back to e 2 pi I over 3 again?
good question. Because Isaac said so. Because this basically gives us a 3 cycle, something that if we did it 3 times, if we just had did this operation, we composed this function with itself 3 times, called this phi sub 1 or whatever. If you did phi sub 1 composed with phi sub 1 composed with phi sub 1, we get the identity function. If this mapped to e to the 4 pi I over 3, then meaning each time you applied phi sub 1, these would flip-flop with each other. Then if you did it 3 times, you wouldn't end up back where you started, and we wouldn't end up with something we wanted to correspond to a 3 cycle in that case.
So this is just gonna naturally kind of fit like a glove. Will there only be like 6 operations in total, and they're all just gonna be isomorphic to S3? Okay.
So let's say we've made this choice. What's gonna have to map to 1, 3, 2? James?
1 maps to 1. Group 3 of 2 maps to e 4 pi I over 3 of 2. And e 2 pi I of 3 maps to e 2 pi I of. It's like a tongue twister.
There's gotta be notation for this.
Perhaps
So
there
I'd say
is.
2 pi I over
But can't we just label them all? We can just like define fee 1 is this one, fee 2 is this one, and then just.
Alright, fine. How about this is fee 2, this is fee 1, this is fee 3.
But that's not fee not, a fee 0?
And yeah, because then we'll go from 0 to 5 instead of 1 to 6, and I don't like the sound of that.
Computer scientists.
Then it's isomorphic to Z-mod.
I ain't a computer scientist. I don't care what Cypher has to say
It's
about
not
this.
isomorphic.
He probably didn't believe any of these numbers exist anyways.
Well, they are called imaginary
The indexing
numbers.
set, I mean.
So, how about, let's go fee sub 4. What's another one? How about 1 maps to 1, cube root of 2 maps to itself, e to the 2 pi I over 3 goes to e to the 4 pi I over 3.
Yeah.
Andrew.
Well, it's gonna be a 2 cycle. And I don't think it matters.
I don't think it matters which one you do. I think once we pick one, the fee 5 and fee 6 will matter very much, but I think this one we could pick any of the 3 cycles and have it work out. So which 3 cycle do you want?
What?
Need 2 cycles.
Okay.
Or did I say 3? I meant
You
2
did.
cycle. Yeah. It doesn't matter which 2 cycles this maps to. This very much cannot map to a 3 cycle because those are already taken. Yeah, that would be one way to do it. All right. How about, which way do I want to approach this? Yeah, we'll start with these. Let's say we map 1 to 1, cube root of 2 to e to the 2 pi I over 3. Cube root of 2. And e to the 2 pi I over 3 maps to e to the 4 pi I over 3. So this time, both cube root 2 and e to the 2 pi I over 3 are mapping to other elements. James?
That has to map to 2, 3.
Why?
Because if you take 1, 2, 2, 3, then that is equal to 1, 2, 3. And if you take V4 and V5, then that is V2 because
Yeah.
the bottom one cycles
6.
around.
You said we're not starting at 0.
Well, no, I'm not defining a new one. I'm writing some. This is something else, okay? I was going to say, how can we write fee sub 5 as a composition of 2 of the other fees that we've already defined?
Oh wait, let's just get the right one. It should be.
Yeah.
I have to work it out still, but I'm going to assume that you did.
Fee 2. No, it's 2
It's
4.
2.
Well, just take
2,
the
3.
composition.
I'm looking for 2 fees, not an element in S3 here.
So,
Yeah, no, fee 2 and fee 4.
Oh.
Let's see, if we start by doing fee 4, that'll map 1 to 1, that bit to, that'll get mapped to that. If we then apply fee 3, 1 still maps to 1.
Wait, V4.
I was looking at the wrong one.
Okay.
If we do fee 2 composed with fee 4, let's see. If we apply fee 4 first, that maps 1 to 1. Fee 2 will still map 1 to 1. Cube root of 2 will map to cube root of 2, which maps to e to the 2 pi I over 3 cube root of 2. E to the 2 pi I over 3 maps to e to the 4 pi I over 3, which maps back to itself as a consequence of this relation. Like so. So here, we need to compose fee 2 and fee 4, what they specifically psi of phi 2 and psi of phi 4. Which, let's see, psi of phi 2 is 1, 2, 3. Psi of phi 4 is 1, 2. All right, Emily Rose, how well do you remember this? Nah.
one maps to 3, I think,
One maps to 2, which maps to 3.
and 3 maps back to 1, so just 1 3.
There you go.
And 2 maps also, because we're swapping.
And then 2 maps to 1, which maps back to 2.
Yeah.
And then phi sub 6, well, phi sub 6 is kind of
The
determined
leftover.
by the
I wonder what it
leftovers.
is.
So 1 maps to 1, cube root of 2 maps to, actually, wait, what does cube root of 2 map to?
E to the 4 pi I.
E to the 4 pi, I was gonna say, what have we not actually used yet? Cube root of 2, e to the 2 pi I over 3 maps to e to the 4 pi over 3.
Yes.
It's gonna get stuck mapping to our last 2 cycle. Turns out that'll give us an isomorphism from the Galois group of x cubed minus 2 to the symmetric group S. If you wanted to do, you could also do something very similar to show it's isomorphic to D3. Replace this with R squared, then like R, and then like S, RS, and R squared S for the other 3. But very similar arguments, just replacing permutations with combinations of R's and S's will give you a very similar looking isomorphism. Questions, comments, concerns? Yeah. You're concerned what?
I'm concerned that it took so.
That it took so long? Yeah. Well, I mean, I wanted to go through and just make it clear. Could have saved some time if we had kind of done some stuff by saying, oh, hey, we know this has to be a non-abelian group of order. We know there's 6 of them. It's non-abelian because function composition doesn't work, which we could have done with an explicit example. What's the only non-abelian group of order 6? Oh, hey, it's S3. Up to isomorphism. So we could have done, and there will be tricks for similar sorts of tricks going forward. Technically, we haven't shown anything. We have not shown that this thing is psi here is a homomorphism, by the way. It's clearly 1-to-1 and onto, but proving that it's a homomorphism is a little bit more involved.
We tried composing 2 fees together to see what we get. Like fee 4, fee 5, or fee 6 together, like just the.
That's full fun. Okay, give me 2 of them.
Compose fee 4 and fee 6.
Okay, so that'll map 1 to 1. So we did P4 goes with P6. Let's see, cube root of 2 will map to that, which maps to back to that, so that'll map to, so we'll get cube root of 2 maps to e to the 4 pi I over 3, cube root of 2.
How do we know it?
Because it maps cube root of 2.
If cube root of 2 maps to itself, then these necessarily are going to map to
Oh.
themselves as well.
Yeah.
Wait, because in 4
Because
it
they're
maps to
separate.
itself, yeah.
And then we'll get, this goes to the other one, which maps back to the other
Wait,
one.
shouldn't it be the other way?
No, that's right.
Whatever.
You do P6 and then P4.
The
Because you
order-
have to read
the order
it
doesn't
backwards.
matter the first time.
Oh, backwards.
So function composition and composing 2 of the S3 elements is the same.
So we get Phi2?
Fee
Fee
3.
P3?
Yeah.
Phi3, yes, I know the difference between a 4 and a 2.
Which, if
Wait,
you do
that
3D
doesn't-
maps to 2, which maps to 1. Yeah.
Yeah, something happened there.
Oh,
Yeah.
wait,
Yeah.
because this should be 1, 2, 2, 3 should combine to give us what?
No, I'm wondering if the second one should have been.
Second one.
If you couldn't have done
That maps 1 to 2. So that gives us the 2 cycle. Give us 1, 2, 3.
Yeah.
Then why don't we have 1, 2, 3?
So-
Yeah,
so-
but we got it
We
for
got-
1.
But when you got.
Yeah, so that and that.
No,
No.
What?
Read
No.
the second line.
The second line,
Oh!
we have a 4.
Yeah, you should have gotten. Oh yeah. Oh, I see. We should have gotten 1, 3, 2. Yeah. No.
Yeah, so
Why is it not
cube root of 2 doesn't map to,
But it
So then
should.
that means
But what
it's-
does it map to?
I assume it has to map to
what it is in V2.
Well, let's see, if we compose phi6 and phi4. I'll be honest, the way I did it in my notes was I stopped here.
That's what I was
So-
thinking,
so-
because it like looked to me
So
like it.
so if
acted
it
out.
maps to e to the 4 pi I over 3 root 2, but then the e to the 4 pi I over 3
I see.
it itself maps to e.
You're right, this does have to be.
2
Well-
pi I over 3.
What?
No,
then-
I
then-
think
Yeah,
Why?
I think the issue is that the 2 cycles depend on the 3 cycles, and we just said we can pick any of them.
That's why, Lincoln, I like your idea better. We should have started with defining it on 2 cycles and then let
Yeah.
the 3 cycles be in terms of that, because then it's a little bit easier to do the computation.
Because I was
Yeah.
thinking about the 2 cycles and
Yeah,
I was
you're
like, I was looking at it in my head.
So we
and I
can
was
just
like, this
swap
doesn't match.
feed 2 and feed 3. and
but can
it'll
we,
be
because the
fine.
2 cycles depended on.
We just defined the 2
No.
cycles by the 3 cycles.
Oh, we did do one of them.
That was
Yeah.
before.
Only that a pickle.
Yeah,
Also,
so it's just
why
V2.
is that wrong, what you just wrote up there now?
Because when you combine those 2 functions,
But why
you
does
should
4
get
pi
rid of
I
4
map
pi I.
to,
So-
why does it map
Or
to
is
itself,
it
why doesn't
E
it
equals
map to?
V2 for the top?
Yes, that should be, that should be,
Because if cube
That should be
root of
V2
2
now.
It
maps
should
to
be,
cube
but
root of
how
2,
do we-
then
Yeah, but we
e to
did
the
that
2 pi
second.
I.
Because in V6, e to the 2 pi I maps to e to the 4 pi I.
I don't wanna spend too much time talking about this, basically,
So-
this
And then what if
ends
you
up being.
do, wait, then what if you do,
Eleanor, I'm trying to figure out why
Yeah,
we have up there that was wrong.
Okay,
No, we have
Because
it there, that was right.
and then
Yeah.
what if you do
No,
phi 5 on
cube root of 2
itself,
should
then you
map
don't
to
get
the
that
4
in,
pi I.
do you?
No,
No, maps to e to
because
2
e to
pi.
the 2 pi I maps to e to the 4 pi I now in these functions, so it should map.
let's see, if we
So
compose
first-
4
so
and
first
6.
cube root of
we
2
do
maps
that.
I don't think
So
that
first
should
cube root of
impact
2
the-
or compose of itself. So after phi6, cube root of 2 has mapped to e to the 4 pi I over 3.
Yeah, Dr. Gerstle, if you map phi
But then,
5 to,
um,
like, if you do phi 5 composed with phi 5, do you get the identity?
No.
No. You should.
Yes, you do.
Wait,
How?
Look, cube root of 2 goes to e to the 2 pi
Oh,
I.
okay, yeah,
On
so
the second
issue is
iteration,
that the,
e to the 2 pi I goes to e to the 4 pi I, then e to the 4 pi I cube root of 2 goes to
Yeah,
cube
it's
root of
just that it's a little bit more complicated than it originally looks, cause these things have weird interactions
You
with each
double
other.
up the
Yes,
cycles, which is
yeah,
why I
okay.
wanted to put
You
the
double
root
up the
back there at
cycles.
the beginning, because then you
I
don't
see,
double up
that
the
makes, that would have made it a little easier
Yeah.
to work with, you're right.
okay,
What do you mean you double up the cycle?
so
So
that
you
e
have
to
to-
the 2 pi I over 3 impacts what cube root of 2 is mapping to.
Oh,
So if you're changing e to the 2 pi I over 3 to e to the 4 pi I over 3, it also has to affect the cube root of 2.
It's not gonna, yeah, this interaction is, these two interactions are not independent of each other, in other words.
it's like
We
a-
still get 6
oh, when that's-
permutations, but
When that's
Yep.
equal to 4 pi over 3,
Yep,
you have to
you have
double
to
up the.
change.
yeah, when we
Yeah.
compose
They're
them, it
ugly.
becomes a little bit, yeah, when we compose them, it becomes a little bit trickier. You're right.
I hate that.
Okay, as we can see, doing actual computations with these things can be a bit of a bugger.
That's what computers are for.
If we don't care about what the isomorphism is, and we just wanna know it exists, then we know that any element of the Galois will act on the roots of x cubed minus 2.
Correct.
So it has to be some subset of S3 that has existence.
I've looked at
That would be the easiest way to go about it, Yeah, we're gonna be building up a bunch of theory that generalizes statements like what you just said, Andrew, that's going to kind of make our life easier. I just wanted to go through one direct computation.
Yeah.
Well, it
And
makes
just
it a lot
to kind of show what it looks like, and now and you've made me regret it. Thanks, Parker.
No, this is
You're welcome.
No, I'm kidding. I don't regret doing this. It does make a good point that that this is
Yeah.
tricky and you have to be very careful.
Yeah, because I didn't think it was straightforward. It didn't map to itself. Otherwise, yeah.
Okay. Any other questions or comments about computing Galois groups? Happy.
So I mean, okay, when you might have answered this, but like when it comes to like if you're composing 5 with itself, where do you map like e to the 4 pi I over 3 again? Because there's no like direct mapping defined.
Back to e to the 2 pi I
Yeah,
over
so
3
these
is
just-
the only
Yeah,
other
You
option.
could just like
You're
those
signing
literally
with
it's just like you go both directions on those.
Yep.
Okay.
Yeah, because this always, e to the 2 pi I over 3 and e to the 4 pi over 3 always have to map either to themselves or to each other.
Okay.
That's kind of from our result from last class that says roots of the same polynomial over Q of your base field have to map to other roots of the same base field.
And technically one is one is part of their minimal
Pick-
polynomial because.
It's not the minimal polynomial, x squared plus, yeah, if your polynomial is x squared plus x plus 1, then these are the only two roots of that.
Shouldn't we define it by like step size then, rather than just like this term goes to this term, even though we can have it
Step
keep going?
size.
Well, like because,
What is
well,
step
because,
size?
well, because I'm thinking about it, like because if,
It's just a 2 cycle versus a 3 cycle.
well, I know, but like if you have like, say you're on this term right here, well then the step size is 2, because what we talked about earlier. This goes to.
You mean like the order of the permutation
The order,
or the step
yeah,
size?
like the order of the
Yeah.
permutation,
I was
yeah.
gonna say like step size makes me
Not
think of like
steps, I didn't know what to
for any
call it,
motion
but like
reasons,
the
but-
order of it, yeah. Basically,
Okay,
I'd probably.
sure. Lots of ways of defining this, in other words,
yeah.
and let's build up some theory that'll make this a lot easier. What do you say?
Do we get a new package?
We are gonna get a new package. Yes.
Yeah. I love it. Package.
Never quite know what this class is gonna turn out like. You always keep me on my toes. All right. Okay, sure.
What did you
Pick some
say?
degree.
I know, I
Pick
would-
some
yeah.
degree 20 polynomial and go nuts with it.
That would be fun.
We're gonna
X
stop
to
at
the
degree
20 minus 1.
Normal.
That actually wouldn't be too hard.
Normal.
That's why I picked it.
That's CMON 20 boom.
And normal
Really?
extension, and then
Is it-
find the roots of excuse.
Or no, actually CMON 19.
Exactly. Yeah, I think so.
Yeah, I think so.
Wait, Demon 9.
Anyways, alright. Next thing we're gonna do is we're gonna talk about a couple specific types of extensions that that field extensions, where if we happen to have both of these types of extensions occurring, we're gonna get some very nice properties in our fundamental theorem of Galois theory coming soon to a Math 415 near you. That being normal extensions and separable extensions. So let's start with normal extensions.
Oh, that sounds
Not quite sure where the term normal comes from here. I think that's just like that at some point, mathematician decided this is a nice type of extension to call it. Instead of calling it a nice extension, we call it a normal extension because normally we want to work with these.
Does it sound rather than analogous to normal when we were talking about ideals?
I'm lying to you. It's because it's analogous to normal subgroups.
Oh.
Like every element
It's a normal extension.
is every element.
Oh boy.
It's the equivalent of ideals.
Well, there's even more direct correspondence in that regard, but that's something we'll see a week from now, or 2 weeks from now. So, it's a normal extension if every irreducible polynomial in k of x having at least one root in L must split completely over L.
So if we have like Q and C.
Hold your horses. Split completely. Okay, sorry, what were you saying, Elmer?
So like Q and C.
Q and Z, for instance.
C.
Oh, it's C. I was going to say Z is not
No,
a
no, no, C.
C over Q would be an example of one of these, yes.
Yeah.
Or
Because
one.
everything's linear.
Or C over C.
But there's
Technically, yes, any field over itself will give you one of these.
nothing. What?
Well,
Yeah,
No.
if it's an irreducible
No,
polynomial,
no,
it will have.
no.
Q over Q does not work.
Q over Q doesn't work.
Q over Q doesn't
C
work.
over C works.
I
R
think
over
that's
R
one.
also doesn't work.
Right, you're right. I shouldn't have said that. I was lying.
Correct.
Slash, I hadn't thought it through. Let's do this one. How about this one?
Yeah.
So here's a question. If you have a rational polynomial that has at least one root in Q adjoin root 2, does it have to have all roots in Q adjoin root 2? Or can you give me a counterexample? I've seen a lot of shaking of heads, but I'm not hearing a lot of counterexamples.
I'm working
coming
on
up.
it.
Isaac?
What about the polynomial in Q that's, I'm just gonna give it by its, like x squared minus 2 times x squared minus 3.
That's not irreducible.
It's gotta be irreducible.
It has to be reducible.
Yes.
Oh.
Because otherwise, basically, it's very easy to break.
Like that.
Like that.
Matthew?
Does x squared plus 1 work? Because you go to the i's?
Well, this doesn't have any roots in Q adjoint root 2, so you have to have at least one root in L in order for it to split completely over L in a normal extension. You could certainly have a normal extension in polynomials in your base field that just don't have any roots in L at all. And in that case, normal extension doesn't guarantee anything.
Oh, so then
Oh.
in that case, I think it is a normal extension.
You think it is?
Yes.
Andrew?
I
X to
totally.
the fourth minus 2.
Oh.
Or wait.
Does that have any
No.
roots in Q and join root 2?
No. I felt like it did. It doesn't.
Isaac?
X squared minus 2 times x squared plus 1
Irreducible, sorry. Needs to be irreducible.
in
Q.
In Q.
Irreducible
X
in,
squared
in over K base field. X squared minus something times x squared minus something else sounds a lot like a polynomial that, even though it doesn't have any roots in Q,
Okay.
is still reducible over Q.
reducible in q of x.
Turns out this is not as easy a question as it might look.
Yeah. Does the polynomial have to be in K? Oh yeah, it's K.
Turns out this is normal.
Weird.
But it's not immediately obvious as to why that is. This is not like something that's like you could very quickly just look at the definition and see.
Is any normal extension or any simple extension of Q going to work?
Well, let me ask you this. How about that one?
Never mind. That one has x to the fourth minus 2. Or minus 2.
So x to the fourth minus 2. Does that have any roots in Q adjoint fourth root of 2?
Yes.
Such as?
Fourth root of 2. And
As a root, fourth root of 2.
but it also has I.
And let's see. Does that factor into linear terms? No. Because there's a couple of imaginary roots in there as well, and this is a subset of the reals.
So all irreducibles in Q, in the polynomial that's in Q, are either quadratic or constant.
Sorry, I was busy writing that down. Say that again.
All the irreducibles in Q adjoint X are either quadratic or constant, right? Or no? No, we don't have that in there.
No. Over the reals, we had a theorem that said that, but not over the rationals. Because I mean, there's lots of. Just take any x to the k minus 2, for instance. K greater than 1. Irreducible by Eisenstein. So it turns out this one is not a normal extension.
But that's also a bigger, has a bigger degree.
True. This is degree 4 extension compared to that degree 2 extension. Your point?
There's at least one root. Doesn't have to be.
So I feel like if it's a degree 2 extension, it should always work.
An interesting hypothesis.
Because you should just have it and it's negative as your roots.
An interesting hypothesis.
I'm gonna keep that hypothesis and see where it goes.
Like it.
Yeah, I mean,
2 is a number that.
it is worth perhaps noting that, the roots of unity of 2 are,
The roots of unity of 2. You're gonna have to explain that one to me.
This is 2 times 13.
for, for z squared is equal to, is equal to 1, you're just gonna get 1 and -1, which are both elements in Q.
Sure.
Whereas at higher orders, you're going to get i's in there. So I don't know. I don't know necessarily whether that'll work, but it would seem to make some sense if we end up with that.
Yeah, I think it turns out, Eleanor, I like your hypothesis. I think it's a good one.
Should we get these?
But if we don't have degree 2 extensions, it becomes a lot trickier. Or heaven forbid, if we have non-simple extensions.
Oh. I don't know.
So it turns out proving something is not a normal extension is not too bad. You just find a polynomial that has at least one root but not all of its roots in your extension. showing that something is normal directly, pretty tough.
Unless it's degree T.
Well, I meant in the general case, but yes. Turns out we're gonna have a nice theorem that makes this a lot easier. Turns out field extension is normal if and only if it's a splitting field for some polynomial in your base field. If and only if L is a splitting field. For some f of x in our polynomial. So splitting fields, in other words, are always, if you take a splitting field over your base field, you're always going to get a normal extension, and something that can't be written as a splitting field will never be a normal extension, according to this theorem. So for instance, take this extension. Can we say that what polynomial is q adjoined root 2 a splitting field for over the rationals?
X squared minus 2.
Yeah, this is a splitting field. Well, technically it's a splitting field extension for x squared minus 2. It's the minimal extension of q over which x squared minus 2 factors into linear terms. And therefore, by this theorem, that would necessarily tell us that that is normal. Something that's much more difficult to prove directly than it is to prove using this theorem. And this, for instance, would give us a nice way of, this theorem would actually give us a nice way of showing that q adjoined fourth root of 2 is not equal to the splitting field for any polynomial in the rationals. Because if it was, it would have to be a normal extension, and we have seen that it is not. Questions or comments related?
I was just
So let's prove this. See if we can get there to prove this. Let's start with forward direction.
15 minutes, man. You can make it.
This is a little bit of a longer one. Not too bad. So let's suppose that we have a finite normal extension to start with. Oh, by the way, what do we mean by finite extension?
Not
It's,
not
it's adjoined to a finite,
Yeah.
finite
from my hydrant.
set.
The degree is infinite.
The degree of the extension is finite is what I'm looking for. Yeah, which is a little bit different. For instance, adjoining pi gives you an infinite degree extension, and we would consider that an infinite extension even though we're really only adjoining one element. So let's let L be a finite extension, finite normal extension. And we need to somehow construct we need to somehow show that we can find some polynomial in K for which L is the splitting field.
I have a question. What does an infinite normal extension look like?
You adjoin pi.
Hey, that'll do.
So it's a little bit tricky to come up with a polynomial when we don't know anything about L and we don't know anything about K.
No, what if we wrote it out in summation notation?
If we wrote it down in summation notation. I don't think we need to do that. Give me a hint. Let's define a basis. L is an extension of K. We know that L can be written as a K vector space, right?
So like,
And it will have a finite basis because it's a finite extension.
What do you know?
Whoa.
With some basis. Let's call it Z1 through Z sub n over K. So these are all elements in L that we say form a basis for L as a K vector space. And I claim we can use these to help us find our polynomial for which L will be a splitting field.
Can we make each one z1 through zn a root? Would that work?
Of what?
Of the polynomial?
Is that going to be?
That's going to be necessary, but not sufficient. So here's what we're going to do. We're going to take a minimal polynomial for all of these over K. m sub I be the minimum polynomial of each corresponding z sub I over k. These are all elements in L. We know L is an algebraic extension because it's a finite extension. So all of these, every element in L, including these, should have some minimal polynomial over k. And here's my question. How can we find a way, how can we use these minimal polynomials to construct one super polynomial that'll have that'll have each of these as one of its roots, plus potentially some other stuff?
What if we multiply them all together and then take out all the redundant roots?
Yeah, we'll just multiply all together. We don't necessarily need to take out the redundant roots.
Well, but all the minimal polynomials are polynomials in k, right? So if we multiply them all together, then the one we finally get isn't.
It's not irreducible, but it doesn't need to be.
Wait, but we just need it to be a splitting field.
We just need a polynomial, and then for which L is a splitting field. But that polynomial isn't. It can be anything theoretically.
We just have to prove that L is the splitting field of this polynomial.
Yep. So we're going to define m of x to be the. Let's use some, not summation, but product notation.
Oh,
Yeah.
Oh boy.
I'm used to that.
There we go. I was going to write out m sub 1 of x, but this is m sub n of x. But you know what? For you, Emily Rose, I'll do this.
Yay!
There's no do.
Nope.
Well, there is, but it's part of this, and I'm not gonna. It doesn't get said out loud.
Pie. Big pie is more exciting than do that.
Can we-
Sorry.
I don't wanna talk about big pie.
So here's my question. Since each m sub I has to split in L, why is that, by the way? Because L is a normal extension, and each of these has at least and each of these has a root. Each of the m sub I has a root in L, namely the corresponding z sub I. And the fact that we have a normal extension means that if you have at least one root in L, then you have to have all the roots in L.
And they're also irreducible because they're all minimal.
Yes, yeah, and they're yes, and we need the irreducibility from the fact that they're minimal polynomials.
Why can we not just use M1 as F for just the forward direction?
Because then we wouldn't necessarily get a splitting. We wouldn't necessarily get a splitting field. It wouldn't give us. It wouldn't because
Just to cover everything that might be.
because the minimal polynomial could potentially have. Hold on, let me stop thinking about this. If we just took m1 of x, took the splitting field of that, then it would have a root, so it would have to have split completely over L.
But L might not be the splitting field because you might be able to get a smaller one, right?
Yes. Well, let's write this out and then talk about that. Since each m sub I splits in L, and this is going to be by normality of L over K, that tells us m of x has to split over L. Because m is just the product of the m sub I. So if the m sub I can be written as a product of linear terms, their product necessarily has to be able to be written as a product of linear terms. So we know that L is a field over which this polynomial splits. And moreover, we can say m of x can't over any subfield of L, any proper subfield of L, I should say. And why is that?
Because we get subfields by like removing basis elements, so you can have.
Yeah, you wouldn't get all your then you'd be losing at least one of your basis elements, and it wouldn't be subfield anymore. since L is generated by the Z1. There you happy partner.
So
Yeah, and I think and I think that's where that's where just having M1 comes into play, and that it would be you would get a field over which the thing splits, but it wouldn't necessarily give you minimality.
Okay.
And thus we can conclude L is a splitting field spectrum.
Split link field.
A what? What did you say?
split link field.
It looks like the second T isn't crossed, so he's saying split link field.
Eh. Any questions or comments about the forward direction? One thing you look like you have something you want to say.
I go on, I can ask later if I actually want to ask it.
Okay. So I guess it's the forward direction. Turns out the backwards direction is a little bit spicier.
Good thing it didn't take us all of our time in the forward direction.
Yeah, well, I'm not convinced we're going to finish the backward direction, but I would like to start it because it comes with a cool diagram. Because here's the problem with the backwards direction. We're going to assume L is a splitting field, and we need to show that it, for some f of x, we need to show that then L over k has to be a normal extension. The problem is, to show something's a normal extension, you have to show that every irreducible polynomial having at least one root in L must split completely over L. Every irreducible polynomial means we can't just show that f of x, can't show that that's true about f of x, which is obvious if it's a splitting field for f of x. We have to introduce another function, g of x, and then somehow do some sort of comparison between the roots of f of x and the roots for which L is a splitting field, and the roots of some other arbitrary polynomial g of x.
But at least we can say that there's one root of g of x in L.
That is true. Well, we'll be able to use at least one root by the fact that we're trying to prove this, and it would make sense to not assume that if we were trying to prove that. So, I'm getting excited. Pressing too hard on the board here. Let's let L be a splitting field. Oh, apparently in my notes I'm letting L be a splitting field for g of x to start. And then f of x is going to be the thing that we test normality for. And we're going to let f of x be an element of k of x, be irreducible. And our goal is to show that if f of x has at least one root in L, then f of x has to split completely in L. Without loss of generality, we can assume f of x has degree at least 2, because if f of x has degree 1, then having
Our job is here is finished.
then having one root in L will automatically mean you have all of your roots in L. So I'm going to say of degree greater than or equal to 2, with root alpha, an element in L. And our goal is going to be to show that f of x splits completely over L. So how do we show that f of x splits completely over L? We have some polynomial, arbitrary polynomial. How do we show that it splits completely in L?
You show that every root of f of x is an element of L
Root of f of x. Root of f of x living where?
in K.
In K.
Sorry.
Well, in that case, then it'll automatically be an L. This is tricky because it's not K because then it's automatically an L. It's not L because well then it's still automatically an L.
Does this proof share any similarity with the proof that all polynomials factor completely over the complex numbers?
Yes. I mean not like super. It's not like it's not just like a direct consequence of that or anything, but it's kind of shares some commonality with it. Yeah. We need to define a splitting field for f of x.
And then show that.
Just call it N.
Oh, we're going to call it E, sir. So let's let E be a splitting field.
Which that's a theorem we might have used it before, I think.
What?
Just the splitting field actually exists.
Oh yeah, yeah. It's basically just repeated application of the theorem that says, given any f of x, you can always make a field extension which that polynomial has a root. Just repeat that in times where n is the degree of your starting polynomial. Yeah, we talked about that in the splitting field packet. So let's let E be a splitting field for f of x. Here's the problem. We're also going to want to. It's going to be necessary for us to have g of x split in E as well. We need g. It's going to be necessary that g of x splits up into linear terms for our proof. So we can't just let E be a splitting field for f of x in that case. How can we define this E in a way that would guarantee f of x and g of x both split?
F of x times g of x?
F of x times g of x. Yeah, exactly. So this is some polynomial that lives in L of x. Because f and g, technically it's a polynomial over k, but it's also a polynomial over L.
Is that f of x is a polynomial now?
F of x times this whole
both of
thing
them. Okay.
is now up there. And we're going to suppose that beta is a root of the polynomial f of x as an element in L. Here's where the fun part comes in. So we got a lot of field extensions going on at this point. Ellie Rose?
Why is beta? Wait, I thought we only guaranteed one root of f of x in L.
No, it's in L adjoint x.
Oh, wait.
So it's in a bigger field.
Beta is not necessarily an element in L. We're saying that f of x is a polynomial over L, and we're assuming beta is a root. Maybe I'll add in here in E of the polynomial f of x, which happens to be polynomial. So here's what's going on. We got ourselves a k. K is properly contained in L. Well, maybe not properly contained. K is a subfield of L. L is necessarily going to be a subfield of E. We get L. Yes, aren't we clever? So you know what else we can do? We can take K adjoined alpha. And is K adjoined alpha going to have to be a subfield of L or E?
K adjoint alpha.
Remember, alpha was our kind of original thing there.
It should be a subfield of L.
It should be a subfield of L.
Yeah.
But we don't necessarily even need that. I'm going to write it over here. And then that is going to be contained in L of alpha, because K is a subfield of L, which is contained in E. And then, we do the same thing with beta. Say K is properly contained in K of beta, which in turn is, I don't know why I keep saying properly, I should stop saying that because none of this properly is guaranteed. K of beta is going to be a subfield of L of beta, this case is a subfield of L, which in turn will necessarily be a subfield of E. Also, L is a subfield of these two things.
Yeah.
This is like
This looks like the
Okay.
Trinity.
levels.
Yeah. And what we're going to get is, we got this fancy commutative diagram going on here. And it's time to play around with the degrees of some field extensions. But we're gonna have to do that next time. I just wanted to show you all this diagram today. It turns out if you just start playing around with like the degrees and various extensions in this diagram, what you end up eventually being able to show is that the degree of L of beta over L has to end up being 1, which ends up showing that beta is an element in L, which ends up proving normality because we've shown that our f of x, which has at least one root in L, ends up having to have all of its roots necessarily in L. But it takes a little bit of work still to get to this point. This diagram
Does
chasing.
that guarantee you
Because
clear
this is the
disarmament?
general,
Say what?
I only wrote the
Guaranteed nuclear disarmament?
This is similar to
why not?
complex, the fact that you can, because it's just the generalization.
We'll finish this proof. We'll finish this proof next time and then talk a little bit about separable extensions. Well, separable, there's not much to say.
No, I just.
So the reason that this has to be context is that we take the forward direction and we can not
Much
you can't
though.
construct an L of X out of an infinite basis.
No, but at least it's 6 instead of 5.
Right.
That would be
Yeah.
Yeah, that's where the finite comes into play, is because, I mean, unless you want to be able to have like your minimal power series instead of a minimal polynomial, that ain't good. See ya.
Does it work with minimal powers?